Let now D be a region defined in this blue area. It's defined by three contours. We have this large contour C. It goes in counterclockwise direction, and we have two small curves inside this C, C1 and C2, and these two contours, they are not intersecting with each other, and they are all three contours are simply simple closed contours. This is the way this domain D is defined. If this is the case, we have a following theorem. Assume that f is analytic. The function f is analytic in this blue area, which we call D. Then the integral over the curve C of f of z is equal to the sum of these two integrals. One integral over this curve C, C1, and another integral over the other curve. That's a very useful theorem. And more generally, we have that if you have many such small curves, C1, C2, C3, and so on, which are simply closed, and not intersecting with each other, then we have a general formula which states that the integral over C, the largest curve which is enclosing all the other curves, are equal to the sum of all these integrals. In the same way, in the same obvious way that we formulate the theorem above. So a corollary of this is that if we only have one such curve, then we have this theorem, or this result. Okay, what can we do with this theorem? It's very useful, in fact, because, for example, if we have a simple closed curve, any curve which is enclosing the origin, then we can take a circle here. It could be the unit circle or some small circle which is inside this large circle, and which is enclosed by this large circle. And the Bow theorem tells us that the integral over this large circle, large curve, is equal to the integral over this circle C1. And it's an exercise 4, I guess. In this exercise we show that the integral over this circle of 1 over z is just equal to 2 pi I.